All right, so let's go through the conduction analysis methodology. All right, so this is like the process that you gotta be able to figure out how to do. You just kind of go through it. It's second nature. Follow these steps kind of no matter what the conduction problem is. So there are roughly 7 steps that I've identified. We'll go through all of them, but just so you kind of know where we're going. So first step, and the goal again is we want to relate heat transfer, which we can figure out from a control volume analysis. You can relate heat transfer to temperature. We're always trying to relate heat transfer and temperature. That's kind of the end goal here. All right, so step 1, let's define the domain. All right, so simplest task usually, but sometimes there's some subtlety to it. So for this, let's again do our plane wall geometry. Plane wall, we've got adiabatic boundaries on the bottom and on the top, right? No heat flow across that. So in this problem, there's really no reason for us to define the domain anything other than x equals 0 at the left boundary and x equals, let's call it L, at the right boundary. So my domain is, in terms of x, I go from 0 to L. There may be reasons why you don't want to do 0 and L, let's say, in your geometry, but it really depends on the situation. Okay, so domain is defined, check. Step 2, draw the control volume. Okay, draw the control volume. Again, we want to think about a couple things here. So first, we're drawing a differential element. It's differentially small. And we have to be careful that we're only showing depth in the direction in which temperature is changing. Right? You don't need to have a differential element that has depth in any other dimension, or sort of finite depth in any other dimension other than the one that's changing. So for this problem, right, I mean, you could draw it like, don't draw this, but you could draw it like this. That's going to show that there's a finite differential depth in both x and y, but we're not modeling y, right? So that's wrong. Instead, what we want to do is erase this. We want to just show finite depth in the x direction because that's where we're modeling the temperature difference. All right, so there's my control volume. Step 3 is perform the control volume. I'm going to call that CV, control volume, energy balance. All right, so here I now have to identify everything that's going in and everything that's leaving, everything that's generated, everything that's stored. Remember back to the first law. So we're applying the first law here. So let's identify all the possibilities. So first of all, I might have, from the left-hand side, I might have heat flowing in, right? So we would call that Q dot, and let's say that Q dot is at the boundary x, right, at some coordinate x. All right, I might have something leaving, right? I can't have anything leaving from top and bottom. Those are adiabatic surfaces. But I have something leaving from the right-hand side. So let's maybe come back to that name, but you can have that leaving. What else could we have in this control volume? Right? We might have internal energy change. So that'd be du dt. We might have conversion from one form of energy to heat. Right, so think like something's on fire, right? Something's burning, or you have some chemical reaction, or you have friction, or some resistive generation, whatever. So we'll call that usually G dot, right? Some rate of energy generation. It's not actually generation, right? It's not coming from nowhere. It's just conversion from one form to another. Okay, and then the other thing is let's make sure we know the differential width we're talking about. So we're calling this dx. So I added dx kind of at the bottom. Okay, so we know we're coming in at q dot x at the coordinate x. We're leaving with something. Let's for now call that q dot at x plus dx, right? So this is a name. It's not saying q dot x plus dx. It is q dot at x plus dx. So we've got everything we need here, right? We're not looking at like shaft power or anything like that. Let's assume this is an incompressible system, so nothing going on there. All right, so we've got our control volume that's ready to go. Let's try to simplify this a little bit if we can, though. So right now we're starting off with 1D steady state conduction. So let's first of all say this is steady state, so that means the internal energy is not changing, just by definition. Let's assume for now that there's no generation. We'll deal with that later, okay? Let's deal with the simplest case first. All right, so we have our simple case. We can write this as in plus generated is equal to out plus stored. All right, remember your first law, energy balance? In plus generated equals out plus stored, and we have to like put the stuff into the different categories, right? This is fairly simple in this case. So we say in, well, coming in is q dot x. Generated, we're saying nothing's generated here, so we'll just leave that off. What is going out? Well, that's q dot at x plus dx. And then nothing's being stored because this is steady state. So, okay, we've done our control volume balance. We've written out the equation. We've come to the conclusion q dot x equals q dot x plus dx, which is boring. Like, this is not very interesting. You can kind of see this from inspection. So how does this help us, right? Like we're trying to get to a temperature equation. We've gotten this far. How does this help us? Well, unfortunately, there's more steps. Okay, any questions on this so far? Okay. All right. So step 3, we're done with that. So let's move on to step 4 here. So for step 4, we need to determine the heat flow at x plus dx as dx goes to 0, right? And the limit that dx goes to 0, this differentially small element. All right, once we determine that heat flow, then we can come up with kind of more useful relationships. So if you look back at our control volume here, we have to kind of make some statement about what we think q dot at x plus dx is going to do relative to q dot x, or we at least need some model for it. So there's different ways that you can approach this. The conventional way of approaching this is to say, I'm going to model that relationship by saying there's a relationship there, but I'm going to use like a Taylor series just to say, all right, I don't know exactly what the relationship is, but let's just use the Taylor series, throw it in there, and see where that goes. So that looks like the following. So we'll say, first of all, remember what the Taylor series looks like. So f of x is equal to the summation n equals 0 to infinity of the nth differential of some function dx to that nth times 1 over n factorial dx to the n. All right, that's the definition of the Taylor series. So you have to kind of hang with me on this, right? Like there's a few steps and it's a little complicated, but when we get to the end, it's simpler, okay? So we have the Taylor series. If we write that out, expand the first few terms, we get f of x plus df of x dx dx, right? That's just the first order part of the Taylor series, plus the second order, which is d squared f of x dx squared times 1 over 2 factorial dx squared. And I'll just continue down here. So d cubed f of x dx cubed 1 over 3 factorial dx cubed, and so on. Okay, why am I doing this? I'm not trying to torture you. what we should look at here is what happens to the second and third order terms and the ones above that when dx becomes really, really small. They basically become unimportant, right? Because you have dx is really small, so dx squared is going to be really, really small. Dx cubed is going to be even smaller than that. So as dx becomes really small, this stuff here goes away. So as long as we're taking a differentially small control volume, we can model the rate of heat transfer, the change in the rate of heat transfer, using this Taylor series expansion with only these first two terms here. This is where our model comes from. Okay, so we're going to now actually plug this in or apply it to our situation. So then we're saying here, if I want to come up with an equation for q dot at x plus dx, I'm going to use the Taylor series expansion, and I'm going to say, okay, I'm going to represent this as q dot at x plus dq dot x dx times dx. So again, like if this is confusing, but stop and think about what's happening. We're saying, I don't know what q dot at x plus dx is, so I'm just going to throw a model at it. We're going to solve for this stuff later. That model happens to be Taylor series. We can throw away the higher order terms, and we're left with this representation. So I know q dot x, I can plug that in and do some operations on it and then predict at x plus dx. Right, that makes sense? Okay. So let's now take this model and plug it back into the energy balance. So recall, from our energy balance, we said q dot at x equals q dot at x plus dx. Right, this came out of our specific problem that we're looking at. This is not always true, but for our specific problem it is. So now let's plug this stuff here. Oops. Let's plug this stuff here into this term. And we're left with q dot x is equal to q dot x plus dq dot x dx times dx. Okay, so we see on both the left and the right-hand side, we have this q dot x term. It actually cancels out. That cancels out. So now this thing is equal to 0. Well, if that's equal to 0, that dx term that's multiplying the differential can also go away. Right? And we're left with this statement, dq dot x dx is equal to 0. So you still may be skeptical as to why this helps us at all. But it does. Okay, so we've now come up with this differential equation in terms of heat that governs our problem. Right? This is actually one of the governing differential equations for this problem in terms of heat. What this is saying, though, in like intuitive sense, is that the rate of heat transfer doesn't change as a function of x. So look back here, right? Rate of heat transfer doesn't change. It has nowhere to go. There's no generation, there's no storage, nowhere to go. So it just stays there as it was, right? So the rate of heat transfer is not changing. Okay. Good, so that's our governing differential equation in terms of heat. Now we have to figure out how to use that. So step 5. How do we relate heat to temperature? And we're trying to get to temperature. So we're relating heat to temperature. We're going to substitute a rate equation. Which rate equation will we substitute? Fourier's law. So Fourier's law, again, for about the 20th time, is q dot is equal to minus k AC dt dx. Be careful at this point that AC is a constant or k is a constant or whatever, that you're accounting for that. But now let's just substitute that in to this, right? So bring this down here and substitute that in. So we're going to say d dx, substituting in that q dot relationship, minus k AC dt dx equals 0. in our case, let's see, we're looking at a geometry where AC is constant, where K is constant, and of course the minus sign, -1 is a constant. So this stuff here can all cancel out. And we're left with the equation d dx dt dx is equal to 0, or d squared t dx squared equals 0. So through those steps, we've now gotten to a point of having a governing differential equation in temperature as a function of x. Right, this isn't yet our solution, because we don't know what t of x is, but we've at least gotten as far as saying, okay, this is the governing relationship for this problem. This depends on your problem, right? This could change based on whether area is changing, if there's other sources of generation or internal energy change, right? It'll change. But this, for our problem, is our governing differential equation. Okay, so that's, let me just, I'll put a box around that, right? So this is our governing differential equation. We'll skip to the next slide here. So step 6, we have to find a solution for temperature. So how do we find a solution for temperature? Let's again take our ODE. So d squared t dx squared equals 0. We solve this ODE. Right, so this is where I was saying, like, it's important to remember how to solve differential equations. We have to solve this. This particular one's pretty easy, so it's separable. We can do the following. So let's take the d dx, the first d dx term, and separate that out. So we're going to have the differential of dt dx is equal to 0 dx. Right, I just took that dx in the denominator and moved it over. And then let's integrate this on both sides. So on the left, integral of a differential is that argument back. So we just have dt dx, and then on the right, integral of 0 is a constant, right? A constant of integration. So that looks like this. So dt dx is equal to c, some constant. So that's progress. We can keep going, right? We're not there yet. We still need t by itself. So let's do the same thing again. Let's take dt is equal to c dx. Integrate both sides. And we get temperature is equal to some constant times x. And let's actually call this C1, because now there's two constants. So C1 x plus C2. Okay. So this is another important step. So we've now just solved for a solution for temperature as a function of x. Is this the entire solution, though? Right? No, because we don't know what those constants are yet. So the next step is going to be to enforce boundary conditions to figure out what those constants have to be. All right, so this is maybe our general solution in temperature. Okay, so let's, the last couple minutes, talk about step 7, which is apply boundary conditions. Apply BC's boundary conditions to solve for C1, C2. All right, so the boundary conditions are something that are not part of the domain, right? We set up the problem. We have like a left and a right side of the problem. That the boundary is sort of what's happening as you just start the domain or as you just end the domain. So because it's not part of the domain, we actually have to do like what's called a surface balance. So we're not doing we're not doing another control volume analysis on the boundary. We're just doing a surface balance. It's looking at what's going in and what's leaving. Another point to make is that the number of boundary conditions have to match your unknown constants. Right, so we need 2 for this problem. And then the last thing I'll say is there's 3 different types. So let me just tell you what they are, give you some examples, and then you'll look at this more in your discussion. So BC type 1 is a condition we sometimes called specified temperature. Right, specified temperature. The formal name for this is Dirichlet. That's an I. Told you everybody was French. Dirichlet. And this is just where you say, okay, temperature at x equals 0 is equal to, say, TH. Right? You're specifying the temperature at the boundary to be a certain thing. So you should be looking for a specific location at which this boundary condition applies, and then the constant that goes with it. That's boundary condition 1. Boundary condition 2, type 2, is a specified flux. All right, so specified flux, the fancy name for this is Newman, N-E-U-M-A-N-N. And this is where you say, let's say Q dot at x equals L, for example, is equal to some constant. So you're specifying the flux or the heat transfer rate at the boundary. It's a different type of thing. Right? You're no longer doing it in terms of temperature, it's in terms of a flux. The last one, BC3, is called matched rate. The fancy name for this is Robin, R-O-B-I-N. And here you're saying, I have a relationship between the temperature and the flux. So an example would be H bar AS T at x equals L minus T infinity is equal to minus K AC dt dx at x equals L. Right, so on the left you see there's a convection rate equation applied at x equals L. On the right there's a conduction applied, and it's saying the conduction is equal to the convection, right? And that's your boundary condition.